right. Nice break, boys. Next. We got fusion power explained. Oh, I'm really excited for this one. Okay. Admittedly, practical physics is not something I was super interested in paying attention. Actually, I don't know if this qualifies as physics or chemistry because I know fusion and fission are the merging together and splitting apart of atoms. But what I do recall about, it's physics. Okay, gotcha. What I do recall about fission versus fusion is that fission is when the atoms are split apart, and that is the nuclear energy that we are most familiar with today. They're the power plants on The Simpsons that you're familiar with, those like sort of ominous looking coney dome shaped things. And fission is where the atom is, a large atom is split apart by firing a neutron at it, I think. The issue with fission is that it produces a lot of energy, and generally it is safe and it can produce potentially infinite amounts of energy, but the issue is that it produces nuclear waste as a consequence of that. Fusion is when two atoms are merged together to create energy by colliding with each other at high speeds, and this is done, I think, in our sun? I think that's how our sun generates energy, I'm not sure. Cooling towers, yes, that's what those weird looking things are called. Thank you. I want to make a black hole. Me too. Aren't they? There was like a fear with the Large Hadron Collider, or like one of the colliders when they first constructed it. There was a fear that we would inadvertently create a black hole that would, you know, like swallow the entire Earth or anything. But I think that the collisions we do are so small that that isn't a risk. And even if we were to create a black hole, it would just disintegrate instantly due to Hawking radiation. I'm pretty sure. So where was I with fusion? Fusion, it's like slamming two atoms together, super high speeds. The pro of that is that I don't believe it creates nuclear waste. So BAP told me there was a breakthrough recently regarding fusion. I did see a couple of news articles on it. I didn't click them on purpose because I wanted to save my reaction for stream. Fusion is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei and subatomic particles. Fission is my Sunday plans. So, now, let's watch the Kurzgesagt video on this, where they will likely explain it far better than I ever could hope to. I like how WordPad gives me a little warning every time I try to open a link. Fusion is when you and your dad do a little dance and form a second, more powerful Saiyan. You ready, chat? Cute!
The fundamental currency of our universe is energy.
Cute!
It lights our homes, grows our food, powers our computers. We can
In
get
short,
it
it's
lots
the
of
holy
ways,
grail of
burning
energy
fossil
production.
fuels, splitting
Exciting.
atoms, or sunlight-striking photovoltaics.
Or wind. The wind is dependent on the weather, so.
But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet.
Aren't batteries like extremely expensive to or like the panels like extremely expensive and like super like fucking annoying to construct and install? Like the issue with solar panels and windmills is that they require building infrastructure we don't already have and reapportioning jobs to like accommodate those things. You guys remember the issue with coal in a lot of you are EU, but there was a big issue with coal workers specifically during the 2016 election, and Trump got a lot of votes this way in that he was promising people who worked with coal and coal mining and coal plants, etc., that they would be keeping their jobs. There's an issue wherein that, at least in America, where these people don't want to lose their livelihoods, and it would take a lot of resources to maybe like reappropriate them to something like wind or solar, and maybe we wouldn't need as many people. Though that's more an issue of labor than an issue of energy. Obviously we should switch to cleaner energy, but it is an issue wherein we could put lots of people out of jobs, and we need to figure out a viable solution to that.
And yet, the sun seems to have virtually limitless free energy. Is there a
couple
way
billion
we could
years worth.
build a sun on Earth?
More than a couple
Can we
million.
bottle a star?
Ooh! Isn't that what the Dyson sphere is? Like to potentially harness the power of a star? The issue with wind power plants is that they look uggers. You're right, Piotr. Agreed, Alex.
The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce
Mr.
around freely.
Electron!
Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot.
Okay, yeah,
Millions
makes
of
sense.
degrees. Stars cheat
Temperature
to
is
reach these
speed.
temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier
Fusion.
nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant.
Guys, if we solve this, if we can solve fusion, could we theoretically get to a point in terms of our civilization where we could potentially like survive without our sun? Like, is that a possibility? I'm not saying create an artificial sun, but say if for whatever reason we would need to retreat underground due to a number of extenuating circumstances, could we potentially use nuclear fusion to sustain ourselves forever? That's a tough one because there's a lot more to the sun than just like less like I know because like with the sun, if we lose its gravitational pull, then we're free floating through space, which also kind of sucks. But we could have a heat lamp and a rock like lizards, exactly. Not so much death of the sun, but if the sun, say we still had its gravitational pull, but it stopped providing light, or if we needed to retreat underground for whatever reason, so we don't have immediate access to its light. The light's still shining on the surface, but we cannot be on the surface for whatever reason. Could fusion sustain us? And the other thing about fusion is that if we harness quote-unquote unlimited energy, that makes interstellar travel possible. Also validates crypto bros. They won't have the environmental issue against them anymore. So we should abandon fusion.
Fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place.
Cool!
These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host...
Guys, human ingenuity is fucking amazing. That is so freaking cool. Did someone say donut? Yeah.
Magnets cooled with liquid helium
I want
to
to
within
eat it.
a few degrees of absolute
Let me eat the plasma.
zero, meaning they host some of the
She was
biggest
working at
temperature
CERN,
gradients
right.
in the known universe. The second type,
Sorry, I missed that.
electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe.
So cool!
The second
That's a lot
type,
of
called
Celsius.
inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse.
Okay.
In fact, one of the most
But this is a
powerful
really
lasers
tiny
in
amount,
the world
right?
is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion,
Sounds like they have a lot of
right
feasible
now,
ideas, though.
it costs more energy to do the experiments than they produce in fusion.
As ScoPro said.
The technology has a long way to go before it's commercially viable. And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth.
Soonish.
But if it gets there, it will be so
Wait, let me read that tweet.
reactor on Earth.
We finished the hashtag fusion, but it won't do the trick. Building hashtag matter/antimatter reactor for hashtag 2030. Hashtag girl.
But if it gets there, it will be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil with no waste to speak of.
Very cool.
This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium,
Ooh.
might be a great substitute.
Look at this Casanova.
Unfortunately, it's also incredibly rare on Earth. But here, the moon
We need to mine the asteroid. Wait, I heard moon.
might have the answer. Over billions of years, the solar wind
No, moon is boring. We need to mine asteroids.
might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for
mining!
helium, we'd have enough fuel to power the entire world for thousands of years.
Nice!
One more argument for establishing a moon base if you weren't convinced already.
Yeesh. That would be fun.
maybe you think building a mini sun still sounds kind of dangerous,
Moon is pensive.
but they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically.
Hashtag Chernobyl. Hashtag girl. Pause at the graph. I can go back.
Safer than most other types of power plant.
No deaths yet. We can beat this record, lads. No deaths for solar or wind either. True. Well, bird deaths. Sad. True.
A fusion reactor is not like a nuclear plant, which can melt down catastrophically.
See, I don't like the point this seems too good to be good, because I feel like that's really like self-defeatist. Like what? Like why do we say that? I don't mean to single you out specifically, but like why do we say that when there isn't a downside we've seen yet? You know what I mean?
If the confinement failed, then the plasma would expand and cool, and the reaction would stop.
Yeah. So
Put
nothing.
simply, it's not a bomb.
Exactly. Nothing bad
The
would
release
happen.
of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment.
Yeah, that's no good.
Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted.
Okay.
So
Still,
we've just told you that
how long
there's
does it
nearly
take to decay?
unlimited energy to be had at no expense to the
become
environment
non-radioactive?
in something as simple as water.
So what's the catch?
So, what's the catch?
Yeah.
Cost.
How expensive.
We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too
Cost isn't an imminent existential threat to humanity, though. Like burning fossil fuels indefinitely is. You know, cost is something that can be overcome.
expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses.
It was fun,
Or
bye.
maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk.
I think it's worth the risk.
Videos like this one take hundreds of hours to make and are made possible by your
Exactly. Cost is fake.
contributions on patreon.com. If you want to learn more about global energy,
Honestly, I need to throw a couple of dollars at Kurzgesagt because I always really enjoy their videos. 12.3 years to decay for, was it tritium? I'm saying that wrong. What's it called?
a few grams of tritium in use
Tritium.
at a
Hey, I got it. Yeah, 12.3 years to decay if it's really minute amounts actually isn't that bad at all. I think we should simply do it. I agree. Like, what a silly thing to put in our way, you know? Cost. The fuck does that mean? You see prospect with unlimited potential upside, and you think investors are gonna go, Do you know how fucking cocky and egocentric these billionaires are? If I were a billionaire, I would be tripping head over heels to get my name on the first mass-produced nuclear fusion energy. I would be a legend. I would be celebrated for ages. Guys, you can eat me after I invest in nuclear fusion. Okay, deal?
The glow is a soup of superheated ions howling around the hollow donut-shaped reactor.
Hollow donut. We just learned about this. Oh,
Then
that's so
the moment of
bright.
fusion happens and ends just seconds later.
Cool!
If it looks a bit like
Man, this cameraman fucking rules. I would never eat you. You're a comrade. Thank you.
science fiction, that's because until recently it was. No one has captured this much energy for this long from fusion.
This is a quest.
so
It
exciting.
matters so much to find a sustainable form of energy for the planet.
So this was in the
And
UK?
over the last few years, we've had a bunch of hurdles, challenges that we've had to overcome. The results today show that we can do that, and we can overcome all those hurdles, those challenges. That's why it's so important to us.
Fusion's potential is huge. It's the process that powers our sun. Its fuel is in limitless supply, and unlike nuclear fission that runs conventional nuclear plants, there's no long-lived waste. With nuclear fission, atoms of radioactive metals split, releasing energy in the form of heat. In nuclear fusion, two different forms of hydrogen fuse together, making helium.
Can we fuse something other than hydrogen? I understand why we use hydrogen, because it's an abundantly available element, and it's like a very simple element, but could we potentially like fuse something else together?
But fusion releases 4 times more energy than nuclear fission.
Sexy.
This is the engineering model of the inside of the jet machine. The temperature needed to make fusion happen is 10 times hotter than the sun, 150 million degrees. So when this thing is running, it's the hottest thing in the...
Right, because with the sun, like, it's so densely packed because it's just so massive that it can, like, it's easier for it to happen. They talked about this in the previous video.
Solar system. So nuclear
but for us, we
fusion
can only
does
harness
have the
heat.
potential to transform civilization, but the practical realities of making it happen here on Earth are enormous. Here at JET, for example, they must use more energy to achieve fusion than they get from it. But it's proven the science and is developing the tools like precision robotic handling needed for the next fusion machine, nearing completion in the south of France. The ITER machine, say fusion scientists, is the final step before a commercial reactor. Only commitment stands in the way.
We have shown them that this can work from an engineering point of view, from a physics point of view. The challenge is there. They cannot hide. But we've shown them that this is possible. Now, take it up and take it seriously.
The truth remains fusion power won't be with us for decades. Too late for the current climate crisis. But given a fusion reactor makes 4 million times more energy per gram of fuel than coal, oil or gas, its potential to create a brighter future is just too great to ignore. Tom Clark, Sky News, Oxfordshire.
That is so fucking exciting. And honestly, if we pumped billions of dollars into this and we actually prioritized and greenlit this, I don't think it's decades away. Guys, what the fuck are you doing? Yeah, with that too late. What a Debbie Downer. Where'd this guy get his journalism degree from? Guys, shut the fuck up. Nobody follow me. Yes, for example, using helium-3 instead of tritium. Gotcha. For other products, the energy gain for fusion isn't as big, so it wouldn't be as efficient. Gotcha. Limitless is in 5 billion years, exactly. It's a couple billion years, you know, it's virtually limitless. At this point, 2050 is not unrealistic. Exactly. And like I said, if we really prioritized it and put a shit ton of money into it, I mean, look at how quickly we developed mRNA vaccines. We were sitting on that research for like a decade plus. Just like waiting to get, scientists were just waiting to get the funding to develop it further. Then the pandemic smacked us in the ass, lit the fire under our corduroys, or however the fuck the saying goes. And now we have mRNA vaccines. We have an mRNA vaccine for HIV. That's an incredible breakthrough. In the 70s, we were to be doomed by the year 2000. Exactly, that's the thing about these models too, is that nobody can predict the future. We don't know what exactly is accurate. I really don't like that these kind of like cynical, like not cynical, but like these sort of catastrophic models get popularized, because it just paralyzes people into inaction. Like people don't think they're gonna live to see their 30s or their 40s, and that just makes people freeze. They don't think there's hope for them. Lit a fire under our ass. Thank you. I'm gonna specify corduroys though. Chat, what the fuck do we do this weekend for stream anniversary? A 48-hour stream. Shut the fuck up, Brad. Bap, if you haven't left yet, can you time him out?
This video is brought to you by CuriosityStream. Even though the cost
Exploring
of solar
why
and
this nuclear fusion breakthrough matters. Oh, did this happen in November? Or October, I should say? I thought this was super recent. I was seeing news on it. I was seeing news on it on my Twitter topics. Yeah, I thought this shit happened like last week. Or they like announced this shit last week.
wind is dropping, renewables might not be sufficient to meet our clean energy demand in the future. However, nuclear power can play a key role in the decarbonization of our energy sector.
The experiment happened end of last year, but results only hit the news last week. Gotcha.
And I'm not talking about nuclear fission. Rather, quite the opposite. I'm talking about fusion. With its perpetual
the donut.
30 years away target. But before you blow your fuse and start leaving your fusion jokes in the comments, there's been a major fusion development that we have to talk about, and it's kind of a nuclear bombshell. Poor choice of words.
Yeah. I was gonna say, for lack of a better term.
I'm Matt Ferrell. Welcome to Undecided. Besides being safer and more eco-friendly, the fusion fuel sources are more abundant and cheaper than fission fuels. And that's because you can extract deuterium from seawater.
Yay!
Well, you can get tritium during the fusion reaction itself when neutrons interact with elements like lithium.
But seawater is a technically finite source as well. And what if we need seawater in the future to convert into drinkable water?
Lithium. Or as Dr. Greenwald put it,
it's a potentially ideal source of energy. First of all, the fuel is essentially unlimited. It's an extremely energy density form of fuel. So,
but it's such a small amount of seawater that it takes to produce about the same unit of energy that like a dozen times more barrel of coal would produce, correct? Like it's a much, I'm thinking like big gallons of seawater, but that's not necessarily the case. It's like a much smaller amount. Yeah. Okay. I have to go back to work, I think. Enjoy the rest of the stream. Bye, Kev. Thanks for stopping by.
A gram of deuterium and 0.3 of a gram of lithium, if fused in a power plant, would make enough electricity for an average American for a full year. And those few tenths of a gram, you wouldn't, if it was in your pocket, you wouldn't even notice it.
That is like insane.
Lint or something like that.
Based on all that, let's go for fusion. We've got our winner. That'd be great, but that's where the running joke of fusion always being 30 years away comes in. Nobody's produced a fully functional fusion power reactor yet. It takes an insane amount of energy to produce the heated plasma. So right now, the power that you put into a fusion reaction is always higher than the thermal power that you get back out of it. To assess how well a reactor performs is referred to as the fusion energy gain factor, or the simple Q with a ratio. Basically, you just want a Q value higher than 1, which is that thermal power break-even point within the reactor. But we're not even close to break-even. The Joint European Torus, or JET, held a record ratio of 0.67. But the National Ignition Facility, NIF, just recently broke that with a Q of 0.7. But it's really important to note that Q isn't accounting for the full power and electricity required to run the facility, and how much electricity it can actually generate from that reaction. Q is just about the thermal power in versus the thermal power out. For the full picture that accounts for all those additional costs and converting heat into electricity, basically producing more electricity than it takes to run the facility, we'd most likely be looking at a Q somewhere between 10 and 25.
That makes sense.
There's a lot of moving pieces. We have to learn to walk before we can run, and hitting a Q of 1.
I feel like once we hit a Q of 1, a Q of 10 to 25 is inevitable, you know what I mean? Once we achieve that 1-to-1 ratio.
1 or higher is us learning to walk. That's why at this phase of fusion research, everyone focuses on just the Q ratio for the plasma reaction itself. Once we hit that, the focus will shift towards overall power.
Imagine getting that calculation wrong.
Power gain. In 2025, the massive international fusion project that's known as ITER is supposed to start producing super hot plasma with a Q greater than 10 in France.
Exciting!
Now, even though the project was born in the 1980s, construction of the tokamak only started in 2007. Once it's complete, ITER will...
Once again, funding could have made this a non-issue, but it's always about cost, and it's always about money. When we have something with a potential infinite uphead, but our Coomer brain leaders don't want to do nothing about it. That's what makes us wait 30 years for this shit. This is why you guys need to instate me as a supreme... Sorry, 40 years at this point. We're in the 2020s now. This is why y'all need to instate me as supreme dictator of the world. Why don't you fund it with your billionaire streamer salary? Q-Talk. I need to be bisexual and own 15 yachts.
Will be the world's largest fusion rig, which isn't
I have
necessarily
commitments.
a good thing. And one of the biggest challenges with MCF fusion reactors is the incredible magnetic field that they have to generate to contain the plasma. Massive magnets ringing the rig, or the donut, create an intense magnetic field. This invisible bubble traps the blisteringly hot electrically charged...
Why do we use big magnets? Why don't we use small baby nanomagnets? Small, cute baby magnet. I've seen how fucking powerful those fridge magnets are. You don't need anything bigger than that. Sounds like you're overcompensating for something. I'm just saying.
Slurry in midair near the center of the reactor. Being kept away from the rig walls, the plasma won't melt them. And just this September, we found out that 2021 is going out with a nuclear fusion bang. The Massachusetts Institute of Technology, or MIT, along with Commonwealth Fusion Systems startup CFS, designed one of the most powerful magnets ever created on Earth. This joint experiment hit on something extremely important: managing to generate an incredible magnetic field with far less power.
Ooh.
To achieve this milestone, they used something called a high-temperature superconductor, or HTS. The major innovation is actually not that new. Back in 2015, MIT proposed using the superconducting tape in their device design, and I mean a lot of it. The test magnet used 267 kilometers, or 166 miles of tape. This material retains superconductivity at high temperatures, which generates a more intense magnetic field. Martin gave me some really nice
So the solution was small baby magnets. MIT, sit down with me here. Sit down with me here. If you had me on site with my little glasses, with my feet propped up, smoking my cigarette, I could have told you that shit for free.
This is something that I find fascinating about fusion development and why it's taking so long. It's taken decades to learn about new materials and techniques that can be applied to successfully control a fusion reaction at scale. Martin brought up a point that I hadn't considered. The advantage of using this material wasn't just about making a magnet more powerful, but also making it more energy efficient.
You can make great experiments, and we're able to get very high fields with copper magnets, but they consume an enormous amount of electricity, enormous amount of power.
So that turned out to be a good deal, as a stronger magnetic force translates into a 10 times greater power generated by the reactor. As a result, the MIT design is meant to achieve net energy gain in a much smaller unit.
If you are able to go to higher fields, you can make the linear dimensions smaller. You can shrink the size.
When you compare it to the ITER system, which uses low-temperature superconductors, the spark reactor that MIT and CFS are designing is only 2% of its size. And that's a significant reduction in construction cost and time.
Nice!
But does it work? The big milestone that MIT and CFS just achieved...
Buddy, I was operating under the assumption for the past 5 minutes that it did work, and you're gonna bookend that entire segment with, but does it work? I fucking hate scientists, dude. It's BAP full offense. Cannot stand your kind.
Their recent test was putting together one full-size magnet and running it through tests as if the full tokamak was built out. That test went extremely well. Just how well?
Nice!
It reached a magnetic field of 20 Tesla. That's the units we use. It's not the highest field ever produced or the highest field,
but really great
HTS
first
ever.
run.
Those were produced in small magnets, but it's the combination of the size and the field that really put it in a class by
really
itself.
Great first run.
The bottom line is that this test proved out the math and the theory behind Commonwealth Fusion Systems' spark reactor design. This test was the final proof and concept they needed before moving on to the full build-out. I don't know about you, but I was supercharged when I heard all about this, and it's not just for my conversation with Martin. After 3 years of research, scientists nearly doubled the intensity of the field, which led to a 10-fold increase in the power generation. That's why the project leaders now herald this to be a key milestone for building a low-carbon, energy-positive fusion reactor. MIT and CFS are now aiming for the stars. In 2025, they'll demonstrate Spark, the world's first demonstration fusion device that creates net energy output.
That's so exciting!
Now we've just got to finalize the design and build the machine, and we hope that it'll be operating by 2025.
That's so exciting!
Producing fusion power.
That's 3 years away! I was thinking about it in terms of like 2020. Oh, 5 years away. No, chat, that's 3 years away.
Sure. I mean, the machines are not designed to be long.
Can we just pause and take a moment? Hold on.
Of the experiment. I mean,
can we just pause and take a moment to appreciate the fact that humanity created this? Like, every single panel, every single like coil, every single object or instrument you see in this machine was incredibly deliberately placed by somebody who has a spongy little thing in their skulls just like you and me. That's amazing.
The machines are not designed to be long pulse. They would have to be considerably more expensive. There would be much more costs up front.
Now I can hear you already. Is fusion going to happen in our lifetimes?
If we produce net power in a device which can demonstrably scale up, that will attract the funding. It'll basically change the narrative from fusion in 30 years always to, okay, this is real, and it would attract the kind of investment to start building out as an industry. So that's our hypothesis. We're testing it. We have fairly audacious goals, but you kind of have to have audacious goals if you want to play in this particular arena.
I don't know if we're still going to be 30 years away from fusion in 4 years. But jokes aside, I believe cheaper and safer nuclear power will be essential for the future of green energy.
Exciting.
While there's still plenty of hurdles to overcome, this recent breakthrough proves that getting unlimited power from fusion may be a realistic and achievable goal sooner than you think.
That's very
So what do you think
exciting.
of fusion? Do you think this recent milestone is a game changer? Jump in the comments below and let me know. And thanks as always to my patrons, and welcome to new Supporter Plus members, David Whitehouse and Robert Clark.
This channel is Undecided with Matt Ferrell. Auspicious, not audacious. Why not both? I actually don't know the definition for auspicious off the top of my head. I think it means coveted. Or it's like a sort of synonym to coveted. Yeah, it is sort of a synonym to coveted. Oh, good job, I am.